Hello. Here are the aims for today's lesson. Firstly, to outline the effects that manipulation of the flight controls have on the airplane flight plan. We are going to identify the ancillary controls, and discuss the effects of their functions. Ancillary just means the controls we wouldn't consider to be the primary or main controls. At the end of this session, you will be able to define attitude when used in the context of flying an airplane. Name the three primary flight control surfaces, state how they are manipulated, and describe the primary and secondary effects of their use. You'll be able to describe the effect of power changes on the airplane in terms of pitch and yaw. And you'll be able to name the 6 ancillary controls in a basic trainer, and identify their location on a cockpit diagram, and explain their function. Let's do some revision on the airfoil from our previous lesson, as it has a big part to play in this lesson. The airfoil is a cross-section of a wing. It has some parts we need to know about and understand. On the front of the airfoil is the leading edge. On the rear of the airfoil is the trailing edge. When we join the leading edge with the trailing edge, we create a chord line. The chord line gives us a view of the airfoil, and how much camber or curve is above and below that line, and that's part of what affects the lift we produce. The direction of the airflow, with respect to the wing direction, is known as relative airflow. Relative airflow is always parallel with, and directly opposite in direction, to the airplane's flight path. The angle of attack is the angle between the relative airflow and a reference line on the airplane or wing, such as the chord line. In practice, a pilot mostly controls the amount of lift being produced through airspeed with the use of power, and angle of attack with the use of attitude. Lift is one of the 4 main forces acting on an aircraft. On a fixed-wing aircraft, it's an upwards force created by the effective airflow, as it passes over and under the wing. Lift acts in a direction perpendicular, at 90 degrees, to the direction the air is moving. Drag is an aerodynamic force on a body, acting parallel and opposite to the relative wind. The total reaction is the resultant of all the aerodynamic forces acting on the wing or airfoil section, and acts through the center of pressure. The center of pressure is the point along the wing chord line, where lift is considered to be concentrated. Let's move forward now and probe deeper into the forces involved in flight. The first force is lift. Lift acts through the center of pressure at 90 degrees to the relative airflow, and the lateral axis, as you can see in this diagram. Acting opposite to an opposing lift is weight. Weight acts vertically towards the center of the Earth, through the center of gravity. Thrust acts forward, along the axis of the power plant. And lastly, drag is a force opposing the forward motion of the airplane, which acts parallel to the relative airflow, but in the opposite direction to the flight path. Let's now discuss the axis around which an airplane rotates around. It's these 3 axes that allow an airplane to achieve flight. The first one would be the longitudinal axis, which acts lengthways. The next one would be the lateral axis, which acts sideways. The third one would be the normal axis, which acts in the same direction as lift and weight. All of these axes operate around a point called the center of gravity. Changes in the rotation of an airplane around any one of its axes is referred to as a change of attitude. Now that we know what attitude is referring to, we can look at how the airplane's attitude is seen by the pilot. To bank an airplane is to roll either wing lower than the other, which commences it turning in either direction. In an aircraft, if we want to bank to the left, we will move the yoke, which is the control column, to the left. This will change the ailerons, which will change the lift ratio of each wing, and this action will bank the aircraft to the left. Likewise, to bank to the right, the same happens when we move the yoke to the right. From the perspective of the pilot, the aircraft remains aligned with their view, so it is the horizon which looks to be rotating. Changes in rotation around the longitudinal axis of motion, which is called roll, is referred to as changes in the bank attitude. To climb or descend in an aircraft, we raise the nose to climb, and lower the nose to descend. Changes in rotation around the lateral axis of motion is referred to as changes in pitch attitude. We'll discuss the controls and surfaces that move the aircraft around these axes. All aircraft have 3 primary flight control surfaces. There's the ailerons, located outboard, on the trailing edge of the wings. The elevators, on the trailing edge of the rear wing, which we call the horizontal stabilizer. And the rudder, on the trailing edge of the vertical stabilizer. All aircraft have 2 primary flight controls. In this aircraft we have a yoke. Some aircraft will use a side stick, also known as a joystick. All primary flight controls will control a surface and an axis. The yoke controls the ailerons and make the aircraft bank around its longitudinal axis. Pulling back, or pushing forward on the yoke or side stick, will move the elevators and pitch the aircraft around the lateral axis. The yoke is always positioned in front of the pilot, and a side stick is in front or next to them. The second primary flight control is the pedals. These are controlled by your feet. They move the rudder and control around the normal axis. The ailerons are incredibly important, as they allow us to bank the aircraft left and right and therefore turn. They control roll along the longitudinal axis. Let's examine how they do that. Let's take a look at the cross-section of the airfoil, and see that the aileron is on the trailing edge. With a neutral input at the yoke, there is even angle of attack on both ailerons. In order to turn the airplane, we need to introduce a movement at the yoke to create a movement in the ailerons. Ailerons move in the opposite direction to each other, as you can see in this diagram. This causes one wing to produce more, and one wing to produce less lift. You can see the left side aileron moving downwards, creating more camber. The right side aileron is moving upwards. This reduces the camber. An increase in camber will produce more lift and a decrease in camber will produce less lift. And so now, we have one wing creating more lift and the other wing creating less lift. The result from this will be the left wing lifting and the right wing dropping down. If we want to bank the airplane to the right and roll into a turn, we can use the yoke to increase the lift on the left wing and decrease the lift on the right wing. And we do that the same as a car, and turn the yoke to the right. This then rolls us to the right to create an angle of bank and turn us to the right. There is a trade-off happening when we do this. The secondary effect of aileron is called adverse yaw. Whenever we create more lift, we will always create more drag. This is an unshakable law. So the aileron which moves downward creates more camber, which creates more lift, which in turn creates more drag. This results in a yaw away from the direction of the intended turn. On the diagram on left, you can see the green indicating the increased lift and the desired direction of turn to the right. On the diagram on right, you can see the red arrow indicating the extra drag created. The orange arrow shows the yaw of the nose, to the left. This is far from ideal when you are wanting to turn to the right. Another secondary effect of aileron is slip and yaw. When we want to bank to the right, we have our lift vector point into the turn. And so that increased lift pulls us into the turn. As the lift is not holding us directly upwards, and it's pulling us across as well now. We slip into the turn. There is now a new sideways component of relative airflow due to slipstream. This has the effect of pushing into the side of the airplane. This side slip force has the most effect on the tail, resulting in a yaw. This effect is self-perpetuating. In other words, the more you have, the more you get. So the more you bank into the turn, the more you get yawed into the direction of turn. This can result in a spiral dive. This effect is responsible for many accidents, and needs to be treated with respect. Let's discuss the elevators next. The elevators pitch the airplane around the lateral axis. So the primary effective elevator is pitch. When you push the yoke forward, the elevator moves down. This moves the tail up, which is an equal and opposite reaction, and the nose pitches down around the lateral axis. Going the opposite way. Pull the yoke backwards, the elevator moves up. This causes the tail to move down, and the nose pitches up around the lateral axis. There are some secondary effects that you will need to know about. We can liken these effects to riding a push bike up and down a hill. Something I am sure we have all experienced at some point. The areas that are affected are airspeed, or how fast we are going. The vertical speed is how quickly we are gaining height. Altimeter measures our height above something, so it is how far up the hill we are. And engine RPM is how fast the engine is spinning. It can be likened to how fast our legs are pedaling us. So as you've experienced, pedaling up a hill takes more work than it does to ride along a flat surface. Likewise, pedaling down the hill is much easier than both. It might even be difficult to stop yourself from going too fast as you descend down the hill. Let's start with the descent. Pushing forward on the yoke causes a pitch downwards with the nose. Much like riding the bike downhill, we will see an increase in airspeed. Vertically we will start to descend. Our height above ground will start to reduce. Our engine will start to speed up. When you climb in an airplane, you pull back on the yoke, and the nose pitches up. Much like riding a bike uphill. The speed will slow down. Vertically you will climb to a higher altitude. And the engine RPM, much like your legs on the bike going uphill, will start to slow down as it takes more effort. This brings us to the final primary control surface, controlled by the pedals, and that's the rudder. When we step on the left rudder pedal, the nose of the airplane yaws to the left. The same happens when we step on the right pedal, the nose yaws right. All this yawing is about the normal axis. So we can remember that pushing on the rudder pedal will yaw the nose to the same side as the pedal, around the normal axis. One of the secondary effects of the rudder is to cause a roll. This effect has been used to land airplanes after malfunctions occurred in the ailerons. When we push down on the rudder pedal, the right one in this diagram, we yaw the nose to the right. That has the effect of speeding up the left wing, as it now has to travel faster than the inboard wing on the right. So we can say that in the process of yawing, the outboard wing is experiencing greater airspeed due to traveling further than the inboard wing, causing more lift and therefore, roll. There are three primary controls: the ailerons, elevator, and the rudder. The ailerons roll the aircraft around the longitudinal axis. The elevator pitches around the lateral axis. The rudder yaws around the normal axis. So the primary effects again are, roll for the aileron, pitch for the elevator, and yaw for the rudder. The secondary effect for aileron is adverse yaw. The secondary effect for the elevator is airspeed, height, and engine RPM. The secondary effect for rudder is roll. So the primary effects again are, roll for the aileron, pitch for the elevator, and yaw for the rudder. The secondary effect for aileron is adverse yaw. The secondary effect for the elevator is airspeed, height, and engine RPM. The secondary effect for rudder is roll. Let's familiarize ourselves with the flight instruments. The cockpit is most often divided into sections to help in identifying our different instruments. We have the flight instruments. These are the 6 basic instruments used. We have the engine instruments, which show us relevant information about our engine. The navigation instruments show us where we're going and how to get there. And our radios show us the frequencies we are tuned to. This includes who we are speaking to, which navigation devices we are tuned to, what information we are giving to air traffic control and other planes, and GPS navigation information. As well, our autopilot information. Let's start with our flight instruments, and get some more familiarity with them. The airspeed indicator is the top left usually. We use it in all phases of flight as well as all types of flying. It basically measures the difference between the static pressure in the environment and the dynamic pressure of the airflow. The airspeed is measured in knots, which is nautical miles per hour. And it's roughly 2 kilometers per hour for every knot. The flight attitude indicator is next to the airspeed indicator in the center. It's also known as the artificial horizon, but really, the artificial horizon is just the backplate of the flight attitude indicator that has the blue and brown colors. The flight attitude indicator gives a representation of the sky and ground in front of us for when we're unable to see outside. Proper piloting involves looking outside to set an attitude, and not with this instrument. The flight attitude indicator is for use in instrument conditions when you can't see outside. Many an instructor has had their hands full, trying to stop someone who learned to fly on flight sim from using this as their reference attitude. The altimeter rounds out the top tier of flight instruments. It is at the top right, and measures altitude in usually feet, sometimes meters. It reads like a clock, and increases are shown in clockwise direction. Decreases are shown in an anti-clockwise direction. All aeronautical charts have the height of terrain in feet, above a reference to sea level. Weather is also measured in this way. The instrument shows tens of feet, hundreds of feet, and thousands of feet, as well as tens of thousands of feet. The turn coordinator is usually around the lower left of this sort of setup. It has 2 parts to it. The airplane symbol in the top section shows the rate of turn we have. The current position on screen shows a rate 1 turn, which we will discuss in the turning lesson. The ball in the tube is the actual turn coordinator. It shows how well the turn is balanced in regards to the side slip, as we discussed earlier in this video. The ball in the center means it is balanced. The direction indicator shows our direction in degrees. It's set off the compass, and works off a gyro system, and needs to be reset periodically. It's much easier to read in flight than a compass. The vertical speed indicator shows the rate at which we are climbing or descending. It also shows a 0 for level flight. It has much lag, and is only useful in confirming you have set the attitude correctly, not in setting the attitude. It has measurements in hundreds and then thousands of feet. It currently shows a 700 feet per minute rate of descent. What you'd expect to see in this phase of flight. Engine RPM is the last on our list. It shows the power output of the engine, and is used in conjunction with attitude to control the phases of flight. For example, for a descent, climb, or to fly level, we set a power setting and set an attitude. And that will give us the profile we need for any of these maneuvers. The important thing is to know your power settings and attitudes. Once you set them and hold them, then you check on the instruments that you are holding it correctly. Other factors that affect the attitude of the airplane. One of them is airspeed. From the production of lift lesson, you'll have a firm grasp of the relationship between airspeed and angle of attack. To refresh, for a higher airspeed, a lower angle of attack is required to maintain level flight. Alternately, for a lower airspeed, a higher angle of attack is required to maintain level flight. The relationship simply shows that at medium airspeeds, a balance between angle of attack and airspeed exists. And the less we have of one of these two, the more the other needs to compensate. So at lower airspeeds, we need a higher angle of attack. And at higher airspeeds, we need a lower angle of attack. Airspeed is an indication of the volume of air being forced over the control surfaces. And the formula for finding our airspeed is simply the dynamic pressure minus our static pressure. And that shows us how fast we're moving through the air. Based on the volume of air that passes over the wings, we'll have different responses in the controls. The way we change the volume of air is simply by changing the airspeed. Low airspeed equals sloppy and unresponsive controls. At lower airspeeds, we have less volume of air passing over the wings and the control surfaces. And so we can assume that the controls will be less responsive. The reverse is true for higher airspeeds. The greater the volume of air passing over the wings and control surfaces, the greater the response. At low airspeed phases of flight, such as takeoff and landing, the controls are less effective and responsive. This you can see in landing videos online, when the pilot is making wild control inputs on approach to land, and there is little response to the airplane. Don't try that in the cruise at high speeds. As airflow from the propeller flows around the fuselage, it places asymmetric forces on the airframe. Asymmetric means having parts or aspects which are not equal. In most light airplanes, the propeller spins clockwise from the pilot's view. That spinning creates a stream of air, from the propeller to the rear of the fuselage. Because the air is already spinning, it spirals around the fuselage, and is blocked at points by the wings and fuselage. The result is a force in the vertical stabilizer, which pushes the tail to the right. This effect is most noticeable at higher power settings, and at lower airspeeds, such as at the start of the takeoff run. Another force is torque effect. Because the propeller is spinning, it creates a torque force, especially at higher power settings. If you've ever held a bicycle wheel in your hands and spun it, you can feel the torque as it spins. You can feel the bicycle wheel trying to spin in another direction. Because of the direction of the propeller spin, the torque effect will move the airplane in the opposite direction. The torque effect will move the wing of the plane down on the left side, creating a roll. Both the slipstream force and the torque forces we've just looked at combine to cause a yaw and roll. Both these are towards the left, and are most noticeable at takeoff. Back to slipstream, and as the air flows from the propeller over the tail, it makes the rudder and elevator more effective. One more point on slipstream. The slipstream follows the airflow of the propeller. It stays close to the fuselage, and doesn't affect the ailerons much, or at all. And so the rudder and the elevator become much more effective at low airspeed than the ailerons. So to summarize our slipstream effects here, slipstream causes a yaw to the left, during a climb and takeoff. This is due to the high thrust and high slipstream, and low airspeed. Right rudder is required to compensate for it. During a level segment, no yaw is required. During a descent, there's a yaw to the right. This is due to the engineers compensating for some left yaw, and so when the power is released, the compensation is still there, but it's not required. Let's now look at the effects of controls when we change power settings. When power is increased or decreased, there is a corresponding increase or decrease in lift. More power means the aircraft pitches up, and yaws left due to the slipstream. Less power applied, and the aircraft pitches down and yaws right. More of the reason the aircraft pitches up or down is in a future lesson. This is a general overview of the secondary, also called the ancillary, controls found in most light aircraft. Study should be given to your particular type, and especially, the Airplane Operating Manual and Airplane Flight Manual. We'll start with elevator trim. It's usually in the center, or overhead. Usually on the control panel, or between the seats. Flaps are used for landing and sometimes takeoff. They allow better forward visibility, as will be explained in later lessons. They also allow more stable flight at slower speeds. It allows a slower speed without stalling. The mixture control allows the engine fuel-to-air mixture to be optimized for a better running engine. As previously discussed, air is thinner and less dense at higher altitudes. The mixture control allows us to reduce the fuel quantity entering the engine, so it is better suited to the less dense conditions. The throttle directly controls the amount of power being produced in the engine. Forward, or in, means you'll go faster. Back, or out, will slow down. The carburetor heat, or Carby Heat, allows warm air to enter at the carburetor. This is the device which mixes fuel and air, if you aren't using fuel injection. This is so that ice doesn't form during periods of lower power settings. Located at the top of the rudder pedals, they allow us to slow down on the ground, the same as a car. Next we're going to look at the elevator trim. Trim is used to relieve control pressure from the elevator. Airflow over the elevator causes a strong force. The elevator can be trimmed, which is to say it's set, so that the strong forces are taken away. This then allows us to relax our input to the elevators, and the attitude will stay where it is set to. Retrimming is used when a power change is made. Once airspeed has stabilized. After a new attitude is set. After a change of configuration, from flap, landing gear changes, etc. Changes in center of gravity, due to fuel burn, passengers changing seats and the like. Rolling trim forward, the nose moves forward and down. Rolling trim control back, the nose moves back and up. Accurate trimming of the aircraft is essential to accurate flying. Most aircraft use a movable trim tab to trim a control surface. The trim tab is moved to fly the elevator into a trimmed position. At the rear of the horizontal stabilizer is the elevator. The elevator is broken up into two pieces. The inboard section is the elevator. And at the very rear of the trailing edge is the trim tab. Airflow aligns the trim surface for minimum resistance. If we pull back on the yoke, we lift the elevator, which goes straight into the airflow. The trim tab moves opposite to the elevator. This adds opposite force to the elevator. It moves in alignment with the airflow. This acts to counter the airflow force. Because it's further from the horizontal stabilizer, it has a higher force. This is due to the longer moment. So it commands the elevator's position. So we can set the trim, take our hands off the yoke, and the elevator will stay in that position. Flaps are movable surfaces, located at the trailing edge of each wing. There are two main types of flaps: plane and Fowler flaps. Plane flaps change the chord, as you see in the diagram. The chord then changes the angle of attack. They also change the chord by changing the camber. Fowler flaps are able to change more of the wings, or airfoil structure. This means it also changes the chord, and the camber. It also changes the surface area of the wing. By being lengthened, the inboard section of the wing now has a different aspect ratio. An aspect ratio refers to the width of the wing, in relation to its length. By lengthening the wing, we increase its aspect ratio. By changing the surface area of the wing, there is now more surface in contact with the airflow, which generates more lift, as was discussed in the production of lift. This increase in surface area helps to re-energize the wing. You can see the re-energizing in the diagram, with the air moving from under the wing, through the opening between the flap and wing. As the airflow moves up and over the flap, it gives new life to the airflow already on top of the wing. In all flap types, drag is being increased. This is due to the less aerodynamic form of the flaps being deployed. So if flaps increase drag, why do we use them? There are benefits they provide at certain flight phases which makes the increased drag acceptable. One benefit is that flaps increase lift, enabling stable flight at slower speeds. They also increase drag, contributing to slower speeds. Flaps also lower the nose attitude, allowing for a better view of features ahead and below of the airplane. So let's ask ourselves when all of this could be an advantage to us. That would be, during landing. The throttle is an important control, as it's used to change engine power. Power is displayed as RPM, or revolutions per minute of the engine. The more times it revolves or rotates, the more power it outputs. Push forward to increase the power, and pull back to decrease the power. Different airplanes have different ways of changing the power. Some have a lever, and some have a plunger type as in this example. Almost always, you push forward for more power. Let's take a closer look at the mixture control. The mixture control changes the amount of fuel that is added to the fuel and air mixture, used for combustion. At altitude, when we're higher off the ground and the air is less dense, less fuel is required. This is due to the thinner air not requiring as much fuel to be burnt. Like the throttle, push forward to increase the mixture. Pull back to decrease the mixture. Note that by pulling the mixture all the way back you will cut off all fuel into the engine. There's several uses for the fuel mixture control. It achieves optimum engine performance and economy. As mentioned, it cuts fuel to the engine to stop it. This is the normal way to stop an engine in an airplane. This is because it ensures there is no fuel left in the fuel lines and decreases risk of fire. It also ensures the engine can't accidentally turn over if there's an electrical problem. Next we'll look at fuel injection and carburetors. These are the items that mix the fuel and air before it goes into the engine. Traditionally, small training aircraft are fitted with carburetors, which mix the fuel and air correctly. Carburetors have a venturi, like we looked at in the production of lift. This increases the speed, but lowers the pressure of the air flowing into it. Due to the low pressures and moisture within the carburetor system, they can be susceptible to building ice in the opening. This ice will end up choking the engine and changing the air to fuel mixture, causing rough running, and if left, it will stop the engine. A carburetor heat control, also known as Carby Heat, is installed on carbureted engines, which takes air from the warm exhaust, and introduces it into the intake air. This should prevent any ice building up. Normally, air that goes into the engine is filtered to keep out dust and any other particles. It then mixes with the fuel, combusts, and is exhausted out of the engine. The Carby heat control is located near the engine throttle, and is pulled towards the pilot to activate it. Using the Carby heat bypasses the filter, and instead takes unfiltered air, warms it from the exhaust manifold, and introduces it into the carburetor to be mixed with fuel and ignited in the engine. In fuel-injected models, there is no carburetor. However, the unfiltered air option is still available and is called alternate air as it is an alternate source of air into the engine, in the case that the filter becomes blocked. In high humidity, Carby ice can occur in temperatures exceeding 30 degrees. You will notice Carby ice forming, by the indication of RPM decreasing. Rough running engine. Possibly the engine stopping in severe cases. It's very hard to detect in low power settings or idle power. This is when it's likely to occur, so take care to use Carby heat as noted in your flight manual and checklists. The brakes on a light airplane operate generally the same way as car brakes. There are toe brakes on each of the rudder pedals, which will operate one brake for each pedal. Applying pressure to the left toe brake will only activate the left brake. The same is true for the right pedal and brake. Applying pressure to the pedal activates the hydraulic line, which in turn activates the disc caliper, which grips the brake disc, slowing down the wheel. There are several differences to the brakes in a car. To activate, you must press the top of the rudder pedal. You must steer on the ground with rudder pedals. Each toe brake only activates the same side brake. You must balance the left and right brake pressure. You must balance the left and right rudder pedals for directional control at the same time. While this is hard to learn, you will have several benefits from this. It will allow better maneuvering on the ground and will help with directional control at high speeds during braking. Let's now summarize our learnings from this lesson. In this briefing we looked at revision on the production of lift, attitude, the axis of motion, the three primary flight controls, and their first and secondary effects, the effect of slipstream, the effect of airspeed, the effect of power, as well as the 6 ancillary controls and their functions. Let's look at the outcomes we set out to achieve. This is the largest lesson, and I believe the most important. The concepts you learn here will form the foundation for the rest of your studies. Extra attention to learn them is highly recommended. Can you define attitude when used in flying? Can you name the 3 flight control surfaces? Can you describe how the control surfaces are manipulated? Can you describe the primary and secondary effects of the 3 control surfaces? Can you describe the effect of power changes on the plane, in terms of pitch and yaw? And can you name the 6 ancillary controls in a light training aircraft, identify their location on a diagram and explain their functions? When you can do all of this, you've successfully learnt what you need to from this lesson. Well done, and safe skies!